group. Yeah.
Do you see this?
You're all machine learning guys who want to win Kaggle competitions and then impress your boss with high model accuracy, right? We will show you how to do this with fancy hyperparameter optimization approaches. So we, that are Marlina, Daniel, Milas, and me. So yeah, I will first briefly point out the difference between grid search and the methods we used, and afterwards we will talk about the data set where we applied our methods, and we will summarize our results. So let's recall what is hyperparameter optimization. So a hyperparameter is just a parameter which has to be fixed before the model is trained. So afterwards it is trained, and we can evaluate the performance of the model by cross-validation. Examples for hyperparameters are the activation function for a neural network or the number of hidden layers. And the function which exactly maps each hyperparameter or configuration to the cross-validation score is called objective function. So in hyperparameter optimization, our goal is to maximize this objective function. So how do we do that? So the naive way, which you all probably know, is grid search. We just go one by one through the hyperparameter space, and in the worst case, the best solution is exactly at the end. So speed up version is random search, where you don't follow a grid, but you choose randomly the points. Nevertheless, you can be unlucky if the randomness is not on your side. It can also take a long time. So the methods we used are smarter. We used tree-structured parts estimator and the Bayesian optimization with Gaussian processes. So in a nutshell, what makes them different from these approaches? So we take into account the whole history of points which we already evaluated to find a new promising candidate. So let's get to data. And this data set is boring, so we decided to choose hiragana. So I don't know how a Japanese guy can distinguish it all. I definitely need a machine learning algorithm to do that for me. So what's the data set about? It's 80,000 images are big, and images are of size 48 times 48, and we have 72 classes. So here the data set was quite balanced, except from 5 groups, so we used data augmentation to take care of these small groups. Furthermore, as hyperparameterization is computational hard, we had first a bit of problems for computation on our laptops, but we finally managed to upload the data on Collaboratory and did the hyperparameterization there. And the third thing that we did, we tried out different representations of the image, so one time as a matrix and one time as a vector.
So what we have two algorithms, hyperparameter, which is TP and Bayesian, with Gaussian processes, and 3 models that we learned that are XGBoost, deep neural nets, and the convolutional neural nets. And as you can see, for each of them, we use different number of hyperparameters. So here like 6, 5, and 2, and and for the first one, we choose XGBoost. And as many of you may know, XGBoost is very computationally expensive algorithm, and for 80,000 images, it's too long. That's why we decided to decrease the size of the images. This is the downsized letter image, 8 by 8, and the blue ones are not important pixels, and 10 red ones are 10 most important pixels. And here you can see the hierarchy of the pixels. Yeah, and some of them are more important. That's why we decided to put them in a separate vector. And this vector we pass to our TPE and the Gaussian processes. And here you can see that both of them actually give pretty similar result. Both of them give accuracy of 96.2%. And this is really cool for us, but actually Gaussian processes here works better because it converges faster to the higher accuracy compared to the TPE. And this is best parameters for XGBoost. Now another model is deep neural nets. For deep neural nets we have actually very fluctuating results, which we find pretty sad, not good, because many configurations lead to high accuracy on Hiragana dataset. And both TPE and here we have like TPE works better on deep neural nets than Gaussian processes. That is cool. Okay. Next one, convolutional neural nets. This is the three-particle estimator on convolutional nets, and here again you can see like okay, you cannot see, but this is 98% accuracy, and it's like slightly fluctuating, but so it's actually not so much fluctuating. It's around like 98%. So accuracy is 98.2%. Yay, we like increased our accuracy. And the last one, our winner, is like Gaussian processes on CNN. It gives us accuracy 99.2%. And again, we decided, despite the computational cost, we decided to run it on random search. And as you can see, it's like not so good. It doesn't converge to the higher accuracy so fast comparing to the Gaussian processes. So what we can conclude from that? We can conclude that for XGBoost, both hyperparameter methods work okay. For deep neural nets, our three-particle estimator works a little bit better. And for convolutional neural nets, our Bayesian method with Gaussian processes works really well because it gives us 99.2%. So our conclusions is that image classification of Hiragana images works both on matrices and vectors. So we can you can pass both vectors and matrices and it will work okay. Another one is that there are different hyperparameter configurations led to high accuracy. This is not what we wanted, but this is what we have. Okay. And the third one is TPE and Gaussian processes evaluate hyperparameter space much faster and quicker, more efficiently compared to random search and grid search. So it's better to use Gaussian processes and TPE, guys. You will have like higher accuracy. And this is our final message to you. Use GPY and hyperparameter libraries to win Kaggle competitions. That's all. Thank you.
So we have at least one project on like hardware part. This hardware part is self-driving.